Great. Well, this afternoon we're hearing from Eric Brynjolfsson, an economist who is a professor here, head of the Digital Economy Lab, and my boss, about a paper he wrote 2 years ago on complementarities and tangibles in the productivity J-curve. A way you might think of it as fitting into the high-level model of task-based automation we saw this morning is that when we invent a way in principle to automate some new batch of tasks, we talked about one kind of bottleneck that's left out of the totally fluid, frictionless model, right? Which is that people might take some time to retrain for the tasks that are still left to labor. But another kind of, the other side of the coin of that is that we might need to put in, or firms might need to put in some complementary work to develop the ways to actually have capital do those tasks that, in the abstract, we now know that it can do. You need to accumulate the particular machines and sort of implement the particular machines that that can perform those tasks. Anyway, I hope that sort of high-level overview does it justice, but we'll hear more about the details.
I got a mic here, so I'm all set. Thanks.
Great.
Okay, it's great. Thanks so much, Phil, for introducing me, and thank you for organizing this. I think this is an incredibly valuable service to the community and the world. I think not to be too grandiose about it, but future historians will look back at this era as a really special time in human history, a really remarkable time. And the reason for that, of course, is because AI is becoming very powerful, and it's going to transform the world, already beginning to transform the world in ways that are just staggering. And so there's lots of really smart people working on the technology side of it, but there aren't as many people yet working on the economic implications. That's why I'm so glad that Phil's organizing this, and I'm so grateful to all you guys to come here and to think a little bit about it and to start working on it. So I'm going to give a kind of a quick high-level overview of a bunch of things. We'll get into the productivity J-curve, but also talk a little bit, just putting things in perspective, and then talking about some of the ways we measure productivity effects of AI in an empirical sense. So, back to the grandiose view of things, through most of history, you can wonder what are the really important things that ever happened. And people talk about empires and kings and queens and plagues. But for the average person, typical person, life really didn't change much from year to year, generation to generation, century to century. Typical person, if you look real closely here, their living standards barely changed at all for centuries or even millennia until the late 1700s. Suddenly things started really taking off. And why was that? So that was something that really was different. And of course, a big part of the reason was technology, in particular, the Watt steam engine. And the Watt steam engine was what we call a general purpose technology, GPTs. We used to just say GPTs in economics, but now when we say GPTs, people get confused. The AI folks have kind of stolen that acronym from us. But Tim Bresnahan and Manuel Trachtenberg said that GPTs, general purpose technologies, are really what drive most economic growth, most history. There are these few very large technologies that have these three characteristics. They're pervasive, they can be improved over time, and they spawn complementary innovation. So the steam engine was obviously one of those. Electricity was a general purpose technology. And I would argue that AI is a general purpose technology, and for all the reasons that are listed there. In fact, I would argue that it's the most general of all general purpose technologies, because what does AI do? Well, AI seeks to solve intelligence. If you go to DeepMind, King's Cross, anybody ever been over there in London? So you go there, and they have this modest little mission statement on the wall. Our goal is to solve intelligence and then use that to solve all the other problems in the world. So I'm sure you each have a little personal mission statement like that as well. But there's some truth to it. If you could solve intelligence, whatever that exactly means, you could do a lot to solve poverty, environmental challenges, health and longevity. Lots of other things could be addressed or even solved if we had more intelligence. And so that's why it's a very special general purpose technology. And the progress is very fast, as you may have seen. Here's some data from the AI Index report that we put out every year, and we update continuously. There are a lot of these charts in there, 500 pages worth or so of these graphics of lines going up and to the right increasingly rapidly on lots of different metrics of these different benchmarks. I asked him for fun to put in that little dotted line there. It's a little bit, not very precisely estimated, but that's basically how well humans do on these same benchmarks. And you can see a lot of them are crossing past human thresholds, and that's kind of a special threshold in many ways. It's a little bit like a boiling point of water. When you've got two ways of solving a problem, and then one of them becomes better, you're going to start switching over to the better, faster, cheaper one, just like water does a phase transition. So we're going to see a lot of tasks switching over as AI is able to do more and more of them. And another report that, if you want to dive in deeper, that we put together last year was I co-chaired a report with the National Academy of Sciences with Tom Mitchell, and David Otter and a lot of other folks were on the committee, economists, computer scientists, sociologists. And so we went through some of the economic implications, including some of the growth implications I'm going to talk about in a few minutes. But there's a lot of other analysis in there as well. So one question that we'll address in this lecture is, has this led to economy-wide gains, these improvements? And a starting point is Halton's theorem, and Phil was just telling me you touched on that a little bit yesterday. So here's one way of describing Halton's theorem. It's basically the change in productivity, total factor productivity, TFP, is the sum of the changes of two factors multiplied together, delta and then dA over A. So what is that? A is the total factor productivity of a particular sector or a particular technology, and the delta is the Domar weight, the share that is. So conceptually, if memos are 10% of the economy, writing memos is 10% of the effort, and they become 30% more productive because of AI, then you multiply 10% by 30%, you get like a 3% gain. And you could do that for all the different places that they're in. So it's a little bit rough and ready, and there's a lot of assumptions that go into that, but that gives you kind of a first order approximation of how much any given technology is going to affect. How many different sectors is it affecting? How widely is it affecting the economy? And how much does it actually move each of those sectors? Pretty intuitive. So we need a couple of pieces of evidence. We need what sectors, what shares are affected. And you talked, I think, a little bit about the task-based analysis yesterday. And then some estimates of the productivity effect, which may vary across different sectors. So we have done some work trying to estimate where AI is effective and where it's not effective. AI, and there's a series of papers that I wrote, Daniel Rock and others, Tom Mitchell and all of this have contributed. And since machine learning and AI is not yet AGI, it doesn't affect everything, you want to identify which places it is affecting. And one way to do that is with the ONET taxonomy. Do you guys know what the ONET taxonomy is? Yeah. So it is the Bureau of Labor Statistics divides the economy into about 950 occupations. For each of those occupations, it identifies a set of tasks. It thinks of an occupation as being a bundle of individual tasks. And we find that you can make more progress by looking at the task level rather than looking at the whole occupation or whole industry. AI could affect different parts of the job, but it's easier the more atomic or narrow you look at the task, the easier it is to assess whether or not you think AI can help it. And so we scored each of those tasks. We did it with humans at first when we first wrote the paper, and then the more recent GPTs or GPTs paper used AI to score them, and that, of course, goes a lot faster, and calibrated with humans to make sure the AI is kind of giving plausible answers. So to give you a little bit more tangible sense of what's going on, one of the occupations in the ONET taxonomy is radiology. And according to ONET, radiologists do 27 distinct tasks. And here are the first 7 listed by ONET. One of them, number 4 there, is one that we all kind of think of a radiologist does, look at images and interpret them to try, figure out, diagnose what's going on. That's a really important task. Some tasks have more weight than others. But they do other things. For instance, they may maintain conscious sedation. And you could imagine that maybe number 4 is something you want a machine to be doing, going and sedating people and they come into the office. Maybe you don't want the machine doing that. Maybe you want to have a human in the loop on some of those. And a lot of the other ones humans do. And if you go through all of the different occupations like we did, what you find is that many of them, most of them, have at least a few tasks that machine learning could really help with. But all of them, we also found, had at least one task that machine learning could not do, or you wouldn't want it to do. And so there's kind of a division. So rather than looking at the whole occupation, doing it at this more granular level reveals that most of the changes are within occupations rather than between occupations. In the GPTs or GPTs paper, they summed these up. We did in the earlier paper as well, but and you could aggregate them by occupation. Here, the horizontal axis, the x-axis, is wages. To the right are higher wages, and then vertical is how much AI is likely to affect that occupation, what share of the task, and how much. And you see kind of an upward slope to it, and then it comes down near the very top. And so what this indicates is that on average, the higher paid jobs are more likely to have more tasks that are suitable for machine learning or they're suitable for LLMs. This is a little different than some of the earlier technologies. You know, the previous wave of computerization had the opposite direction where mostly less skilled workers were more affected, clerical workers were more affected. And in fact, it led to a widening of wage inequality. This one could go the other way. Yeah?
We were talking about task-based models.
Yeah.
The approaching the old task very different. Labor is actually variable in the context of radiologists. What is your that as long as that setting there always labor augment?
It's more complicated than that. But you're right that if there remains some tasks that humans are essential for, then it could easily be labor augmenting. It's not automatically labor augmenting, but it easily could be, because even as you make some of the tasks cheaper, you still need the humans for the other ones. And a lot's going to depend on I think one of the most important factors is in practice is going to be the elasticity of demand for that task. So let's take radiologists, like you mentioned. If the cost of medical imaging goes down because of AI, then you might spend less on medical imaging, or you might spend more. Why might you spend more? Well, if you have downward sloping demand curve and the demand curve is fairly flat or elastic, then a lower price leads to greater quantity. And so while I might not go in if my shoulder's sore, if it costs $2,000, if it costs $200 or $20, maybe I do go in. And so if for every 10% decline in price, there's more than a 10% increase in quantity, you end up spending more. In practice, that happens a lot. I think most people have the intuition, sometimes I even have the intuition, that when the price gets lower, you're going to spend less. In practice, in many cases, you spend more. I mean, a couple of real world, I don't know for sure what's going on with radiology, but I can tell you with coding, coders used to be much less efficient 20 or 30 or 40 years ago, writing a machine code or assembly. Now they're much more efficient, but we have more coders and a lot more code being written now than the past. Will that continue for the next wave? It depends, because the elasticity could change. Jet pilots are much more productive than the pilots, with propeller planes. But we have more jet pilots. How many of you guys flew here? Yeah, I mean, you probably wouldn't have if flying wasn't as cheap. So that's a bit of a longer answer than maybe you were hoping for, but it can go either way depending on that. One of the things that's going to be very interesting that some of you can work on is to understand better what the elasticities are, and maybe even some of the underlying theory about when it's likely to be more elastic, when it's likely to be less elastic. That will be a predictor of which occupations are likely to grow and which ones are likely to shrink, even if all of them have productivity improvements. Now, you take the extreme case, which I think you mentioned briefly in your question. If AI can do everything, then there's nothing left for the human to do. But we haven't seen that with the current wave of technology. Never say never, though. At the end of my talk, if we have time, we'll talk a little bit about more powerful AI, transformative AI, we sometimes call it. I guess is that the name of the program here, transformative AI? So that was the tasks that are being affected very quickly. But so you can use this methodology, and you can do it with ONET. You can do it with other taxonomies. Daniel Rock and I are working on. We're scanning through hundreds of millions of job postings and doing natural language processing (NLP) on them, clustering and identifying new tasks, hundreds of thousands of tasks rather than just 18,000 like ONET. So you can make it more and more fine grained. And this is sort of where the current frontier is understanding in more detail what are the tasks that are actually being done, different ways of getting that, and automating that as opposed to ONET, which is kind of a handcrafted taxonomy and a little bit out of date at any given time. So you can do more to identify where things are being affected. The other side of it is what is the productivity of specific tasks. And I'll dive in a little bit here for a few minutes in measuring that the way we did it in one of the papers with Lindsay Raymond and Daniel Lee. And then we'll broaden it out a little bit. So we looked at how LLMs were being used in a call center. This is one area where LLMs have been incredibly effective. And a company called Cresta came out of here at Stanford, let us work with one of their clients and look at all the call center operators. The LLM was not replacing them. It was augmenting them. It was helping them answer questions. It would give them, when a call or a text message came in, the LLM would give them a suggested answer, and the human could ignore that or use it or do their own, whatever they wanted. And so we estimated, the nice thing about this was that they did a staggered rollout. They did not give it to all the agents at once. They gave it to different subsets of agents over a period of many months. And the reason for that was it just, they didn't have the capacity. And this created a way to get some identification, since the rollout was just staggered across the news. You can compare people who got the technology to people who didn't, even in the exact same time period. So you have a variable to control for time, for the agent. This is the effect of AI. This is all the other variables that might be important, and an error term. And then you could have different metrics. Like, for instance, one of the metrics is resolutions per hour, a measure of productivity. We actually looked like a dozen different KPIs, we call it, key performance indicators, including customer satisfaction, how happy the employees were as well. And what we found was in almost all of these metrics, there was a very noticeable sharp increase. So here's a difference in differences estimator. And you can see there's not much of a pre-trend there. Once the technology is introduced, within a few months, they started performing significantly better. You can do all sorts of different DID estimators. We get kind of the same answer, so that's good. That's the big literature about how to do that. One of the more fun, let me just say a little bit more about the returns. So we looked at a lot of these different metrics. We found it for most of the productivity metrics, or all the productivity metrics, in fact. We also found it for customer satisfaction, how happy they were. We looked at the language of the thing. So you had these millions of transcripts. You could do NLP to see the customer sentiment, basically how many happy words versus how many angry words. And what we saw was a big improvement in customer sentiment. The customers had nicer things to say when they were working with the AI agent. And then the employees also seemed to be happier. They were less likely to quit. There was less employee turnover. Customer service is a place, call centers is a place where there tends to be very short tenure, like the average tenure is like 5 or 6 months. And that improved significantly when they were using this. I guess they were happier when they were working with happier customers and were able to solve problems faster. But one of the other interesting things, there are a number of things from this paper, was that different people got different levels of benefit. So these are the new agents, 0 months, the agents who've been there for a few months, and then the very senior people who've been there for 12 months or more. And you can also do another way of slicing it by how well they were performing before the AI was turned on. These are the people who did the worst, and these are people who did the best. In both cases, the less experienced and the less skilled workers got the biggest gains. So, the less experienced people had a gain of almost 40% there, and the least skilled workers had a gain of almost 30% in terms of performance. The most skilled workers, these are error bars, The most skilled workers, you couldn't really see any measurable benefit. That's the top quintile, the top 20%. Does anyone have any hypothesis as to what's going on there? Why might that be? Yeah, in the back. You say your name, and we'll all get to know you a little better. Right? That's right. Yeah, I think that's exactly what's going on. Is that this system, it has to learn from somewhere. The AI system it's a machine learning system, and the way machine learning systems work. Well, let me take a little diversion, then we'll get back to your point. Traditional coding systems look a little bit like this schematically. You have some inputs X, and you have a program or function f of X, and the computer combines them and gives you output Y. And all of you guys have written code many times like this. And to make this successful, you really have to be precise about the f of X. If you write your code incorrectly, it doesn't work, it's going to crash, it's not going to give you the right answer. You really have to know what you're doing. You have to understand the problem you're trying to solve. And that's the way computers have worked for 70 years since the beginning. And it's worth trillions of dollars. Lots of big companies have been successful. So it's a great paradigm. It's not what machine learning does. The way I think about machine learning is that you take the inputs X and the outputs Y, and you put both of those in, and the machine figures out the f of X. So the machine learns of f of X. Instead of us figuring it out, it figures out. So it knows the pattern. It understands what does it take to give you a good answer. Or it understands what do you need to look at to recognize cancer on a medical image. Or is this a dog or is this a cat? Or is this tax fraud or not? So the machine learns it. But in order to be successful, it has to have lots of data in X's and lots of data for Y's. And then it could be some kind of process in the middle. It could be a deep learning neural network. It could be regression analysis. It finds a pattern there. So back to your point, Maxime, the machine learned from the good answers. And where did it get the good answers? It got it from the good employees. And so the good employees were basically getting their own answers back to them, whereas the new employees were actually learning something new. And so the machine was actually helping the less skilled workers more than the more skilled workers. Did you still have a question there? Yeah. Mm-hmm. Yeah. That's a great question. What do you think? We're certainly faster, yeah. Cheaper. But could they actually give you better answers? What do you think? Mm-hmm. How could it be better at chess? If it's, yeah. Okay. So that's a different way. So it's creating its own Ys. It turns out, you're absolutely right. It also turns out that if you only train it, if you take a chess program and you train it on a bunch of people who have ELO scores of 2,000, that's like pretty good, I guess, the chess program will be better than 2,000. Why? Because it's kind of averaging out all these mistakes. There's lots of different ways to be a 2,000 chess player, and it will find the better. So, but then on top, so there's two ways it gets better than human. One is it can understand the underlying patterns that those chess players have, and then extend those. Secondly, in the case of chess in particular, or lots of games, if you have a way of generating the X's and Y's, then instead of just collecting them, you can make new ones, and you can test those and see if they work. And you guys have heard of AlphaGo versus AlphaZero. AlphaGo learned from previous games of Go by human masters. AlphaZero started with zero data, and it just played against itself, and it said, oh, this game wins, this one loses, and it fairly rapidly, because of their clever coding, figured out the patterns, and both of them got to be better than the best human. And so for that second approach, though, you have to have some way of generating the data. And right now, there are some domains like games, mathematics, coding, where you can generate data. There are other domains, economics, I don't know, where it's been harder to do that. But if some of you figure out good ways of doing that, then we could expand it in those other areas. I'm sorry, was there another question? Yeah. Yeah. So we have seen that happen. In this particular one, there's also some of the measures was time and so forth. And on average, there was not much of improvement for the best workers on any of the things we measured. We didn't measure happiness. Maybe there could have been that. But there was a study recently. I think I'll mention. Actually, it's coming up here, so I'll mention it. So let me just hold that thought. Then, if I don't say the word meter and meter study, then remind me to say it. Part of the way you can see that they're learning from the less skilled workers is that if you look at the language, the words being used, so NLP is a great tool you can do. You see that the less skilled workers and the more skilled workers use different words. They don't use the same stories. They don't use the same examples. But the more they used the system, the more similar they became. So the similarity went up there. And these red dots are when they're using the system, and you can see they're higher up there. So the less skilled workers are becoming more like the high skilled workers. They're kind of imitating them. So that's also consistent with what we were just saying. But there are lots of other studies. This is just one study. There are more and more of these studies. Maybe some of you have done or will be doing some of these studies. And I won't go through all of them, but many of them find a similar pattern of significant improvements in productivity, sometimes 100% or more. In the first 4 listed up there, the 2 on the left and the first 2 on the right, they also had the less skilled workers became better off. But this is not, I'm not sure this is a universal pattern, but it is a common pattern. And then, so this one over here, they actually became worse, according to it. And they're trying to figure out what was going on. Now, it wasn't a huge experiment. There were only 16 developers, and they were relatively new. They gave them this technology and said, here, use this. And it seemed like it took them a little while to get comfortable using it. But when they interviewed them, what was going on is they used the technology to try to write code for them. And while the machine was writing the code, they went off and watched YouTube videos. And so I guess that's more fun than writing code. Then when the machine was done, they were still watching the YouTube videos. And they wanted to finish their video. And so there was a little bit of on-the-job consumption, I guess you could say. And maybe if you measured that, you would capture some of it. Or maybe you could say they had to kind of learn how to change their work processes and habits to take better advantage of it. Interestingly, when they interviewed them afterwards, they said, did this system speed up your coding? They said, yes, it sped it up tremendously. But when they actually measured the time, it had slowed them down. So it's a little bit of a discrepancy there between self-reports and actual results. Yeah. Are just as good. Yeah. They did, on average, both groups stayed. There was some turnover. There were some people who didn't like working with the machine, but it wasn't clear. I didn't see a clear pattern between the more experienced and less experienced. There's just some people who just didn't like it. But most people did. On average, people liked it. On average, people stayed longer. The bigger concern was actually less with the workers. Both groups seemed to like it, or all groups seemed to like it. But the managers said something troubling to me. They said, hey, since this system is making the less skilled workers perform just as well as the good workers, we don't need the good workers anymore. We're just going to hire lower paid people, inexperienced people. And I didn't think that was a good idea. What do you guys think? So my concern is that there's like constant learning of ways of answering questions and the products being updated. And you need somebody to come up with good answers. Until we get the alpha zero of customer service, you need to have the humans come up with the good answers. So arguably, the more skilled workers are even more valuable than they were before. Previously, they were answering a question for a particular customer. That's pretty valuable. Now they're answering a question for that customer and helping all the other customers. So that's even more valuable. So I told the manager, you've kind of got it backwards. Actually, your more skilled workers are even more valuable than they used to be. Yeah, that's an interesting, subtle thing that, whether it's the machine or even another person, if you're kind of like, you get this pile of code and you're trying to figure out what's going on. Yeah, I was talking to Surya Ganguly here, and one of his students gave him some code. They couldn't figure out the bug. And they finally found it. And he said, wait a minute. Did you write this code or did AI? And he said, well, AI did. He said, I knew it because this is a bug that no human would ever make. It's just like a totally alien, weird bug, And so he just didn't even think to look for it. And so, yeah, it is a little, not just if someone else wrote it, but especially if an alien intelligence trying. So for all those reasons, yeah, you got to be careful. You have to think about it. I think a lot of it, I'd put a lot of this in the category of sort of learning curve, though. Like you figure out better how to overcome those kinds of challenges. But people like Ilya Sutskever says that machines can write code so rapidly. But you really think of there's 3 stages. There's figuring out what you want, asking the right questions. There's executing that, and then there's verifying. And he says that now the first and third are becoming much more important, and the middle part's getting compressed, but you still need to do the other part. And in his view, and in my view as well, humans have a relative advantage in the first and third, at least circa 2025, compared to the middle one. Yeah, question, comment. Say again, because they're not owning it? Oh, you mean like own it, like in terms of like getting profit so they get a returns from it? Yeah. No, the benefits go to other people. So now we need to think about updating our incentive systems. If you're only paying them for answering that one question, they're not doing it. But maybe you should, give them IP or property or whatever. Maybe you should pay a premium for people who come up with an answer that's used widely throughout the organization. So it suggests there's some organizational redesign that is needed to take full advantage of this well and changes the incentive. Because otherwise, yeah, I see your point. Maybe there's not really been. And I think this is a more general point, that as these new technologies come along, you may need to rethink your incentive systems, your property rights, firm boundaries. A lot of things may need to change to take full advantage. And when we get into the complementarities part in a minute, that'll become more apparent. Let's take one more question, then I better move ahead. There was a question over there. Yeah, sorry, what's your name? Well, that's a really interesting point. And so let me talk about that. In most of these, as I was describing, the lower performers did better, benefited more, because the top performers, maybe they're already maxed out. And I'm trying to think, but there were some cases where the better performers benefited a lot. And I'm trying to think about the distinctions between them. And I think if you're in a project or task where there's sort of a natural ceiling, once you've reached that, I guess by definition, you're not going to get better than that. So the AI is not going to increase their performance. But if you have something where you just keep getting better and better, maybe something that's more creative or scientific, then the AI could be helping the best performers as well as the less good performers. But in these particular ones, there did seem to be kind of a max. But that's an area of research. That's a speculation on my part right now. Somebody could study it more carefully. So how much is this all adding up to productivity in the economy more widely? So Bob Gordon and I sometimes have debates. He's kind of a skeptic about these technologies and a lot of other technologies. And he's made the point that actually productivity is not picking up. In fact, the rate of productivity growth is slower than it used to. Back in the 90s and early 2000s, it grew about 2.6% per year. Since then, it's grown less than half as fast, not just in the United States, but in 29 out of 30 countries. They've all slowed down quite a bit. So it's a widespread pattern. I just checked the latest data for the United States is 2.4%. That's nice, pretty good. But the quarter before that, it was negative 1.5%. So it kind of bounces around a little bit. I wouldn't go by just one quarter or 2 quarters. It's kind of early to say whether there's any evidence of it picking up. It certainly hasn't in the past few years. So this is what some people call the productivity paradox. I sometimes call it that. Bob Solow, who's an advisor of mine at MIT many years ago, had this great phrase: we can see the computer age everywhere, but in the productivity statistics. Back then, people were very excited about the potential of IT and computers, but it wasn't boosting productivity in the 70s and 80s. And so that led to what I call the productivity paradox. More recently, Daniel Rock and Chad Severson have written about what I just showed you, that productivity is not jumping up despite some pretty cool technologies. So what's going on? There are a lot of reasons. We talk about them in the paper, but I'll zoom in on this idea that AIs are general purpose technologies, and especially this third point about spawning complementary innovations. And as we were just talking about with kind of rethinking your incentive systems, your IP, your organizational structure, your ownership, to take full advantage of technologies, you often have to do that kind of organizational redesign, or it could even be counterproductive. And so those kinds of changes take a while before they have a full effect. And Paul Milgram has called this the Le Chatelier's principle. It's this idea that if you have a bunch of components of a complementary system and some of them are held fixed, then when you change the other ones, you don't get the full effect until the ones that are held fixed also have a chance to adjust. And so if there's some components that are slow moving, that's going to spread out the gains over some period of time. You get to a new equilibrium, changing just one of the components isn't going to give you the full benefit if they're all complementary with one another. And that means that businesses will tend to overestimate the benefits because they don't usually take into account that all these other components also have to change. And that can take some time, take longer than just installing ChatGPT on your computer. So one example of that that really kind of helped me understand this well, I'll relay this to you, is what happened with electricity. When Paul David studied the introduction of electricity in America's factories in the 1880s, he got the records and he looked at them electrifying. They used to have a big steam engine, they put in electric motors, and he went to see what happened to productivity. And he was surprised to see that there was basically no productivity gain. And this happened for year after year, decade after decade. It took about 30 to 40 years, long enough for a generation of managers to retire before you started getting these big productivity gains. Ultimately, later, you did get big productivity gains. But what was going on? Well, the old factories, the ones that were built around steam engine, you have this one big steam engine in the middle of the factory, and all the machinery is powered by pulleys and crankshafts and wheels all throughout the organization. And all the machines have to be kind of clustered around this central power source because you can't make the axle too long or it'll break. When they put in steam engines, what did they do? Well, when they put in electricity, what did they do? They took out the steam engine and they put in the biggest electric motor they could find, right where the steam engine used to be. They hooked up all the same pulleys and crankshafts. They were back in business. Nothing much changed. Productivity was, kind of the same, maybe a little bit less smoke, maybe a little bit less reliability. It was just sort of, wasn't a big change. Fair enough, they were retrofitting factories. Now they started building entirely new factories from scratch. What did they look like? Just like the old factories. They just took the old blueprint. Some architect or engineer made a big X where the steam engine was and put electric motor here instead. And they went off and built it. Not much of a productivity gain, same thing. It took 30 to 40 years. Finally, after 30 to 40 years, you started seeing a new kind of factory and a lot more productivity. The new factory didn't have one big engine in the middle. Instead, they realized, wait a minute, every piece of equipment could have its own separate electric motor. You can make electric motors medium. You can make them really, really small. You guys have probably seen little tiny electric motors. You can make them big. You make them fit whatever piece of equipment you need. And now you're freed up. You don't have to have all the equipment clustered around the power source. You have it laid out typically on a single story, kind of like this, sometimes several acres big. And the pieces of equipment were laid out based not on which one needed the most power, but based on something else. The flow of materials, assembly lines. Now, did you get a productivity gain? Yeah, you had like a doubling or tripling of productivity, like 200% productivity gains. So what's the lesson? Was it that electricity really was just sort of a fad? It was not really very important? No, electricity was important, but only when you combined it with that complementary business process redesign. That's what really unlocked most of the power of that technology. And there's many examples and stories of this. I won't go through all of them. Similar things happened with internal combustion engines, with the internet, with early computers. And the thing is, these complementary changes do sometimes take years or decades for people to figure out. When I was a grad student, I went to Harvard Business School library, Baker Library, and I read these old books they had there from like 1907, describing what they call the big debate between unit drive and group drive, and whether or not you should kind of have all the machinery powered by one piece of equipment or have a separate engine and all that. And it was like a raging debate. It took them a while to figure out what the right answer was. So this is still going on with computers and with AI. 90% of the investment is these organizational and human capital intangibles. only 10% is the actual equipment. But most of the intangibles are, well, they're intangible, so they're not very visible. People don't really think about that process change. And that's really what's driving a lot of what's going on. So empirically, we've done some papers where we measured this. Like, for instance, we found that if firms have higher IT capital and they had big changes in organization, then they got really high returns. But if they had one or the other, 3 of the 4 quadrants really didn't have much of a payoff. You really had to have the combination of reorganization and IT. So if GPTs like AI or electricity require complementary and tangible investments, then we need to think about what that implies. So first implication is that GPTs are going to be associated with a big increase in intangible capital stock or change in it. The effect on those metrics is going to be dependent on whether or not you measure the intangibles. And in many cases, intangibles are not going to be measured. And that means that TFP is going to miss that contribution to output. Even though it's costly to create those intangibles, they're not going to be part of measured output. We don't measure them very well. Let me give you one more concrete example of that. I was helping Michael Dell, and Dell were setting up some new factories. They need to double output. And to oversimplify the story, they had a couple of options. One was to take one of their factories and copy it, replicate it, twice as many bricks, twice as many machines, twice as many workers, and they get twice as much output. Pretty straightforward. Another option is to take the existing factory and apply a lot of process redesign, make it more efficient with new software, ERP systems, and rethink the relations with the suppliers. And with the same factory, they could get twice as much output. Either way, they've doubled their output. I would argue either way, they've doubled their productive capacity. The first way is all going to show up in GDP. You're going to measure all those bricks and machines and everything. The second way, the intangible way, most of it's not going to be measured. The second way is adding a lot to our productive capacity, but not in a measured way. That's essentially the challenge, is measuring the intangibles the way we measure our tangibles. I think that either one of them should be counted, but only one of them is well measured. Question?
So
yeah.
Why is the other way like measured by like how much it takes to
It is. So yeah, that's a good question. It's a question of whether or not it's measured as a capital stock or a flow. So you're paying for that, but it looks like you're spending on expense when you're actually creating an asset. So that's the difference. At the end of it, you now have a factory that can produce twice as much output. So you have an asset, but that's not accounted for. It should be.
It's going to look like just a 50 as opposed to capital investment.
Well, that's a good question. Will TFP increase or be underestimated or overestimated? And it's actually a little subtle what's going on. So let's go through. TFP will be underestimated to the extent that these tangible inputs are used to build up intangible stock. So you're not counting all this new capacity. So during the investment period, we're creating some unmeasured output that's not counted. It should be counted, I think. But afterwards, it's going to be overestimated. Now you've got this asset that's generating twice as many computers, and now you've got, it looks like your TFPs or your output's coming out of thin air. It's actually coming from the investment you made earlier. So it's first overestimated. It's first underestimated, then overestimated during the harvest period. Depends on whether you're building it up or using it. If you're adding it at exactly the same rate as you're using it, those two effects exactly cancel out. So in a steady state, it's neutral. So where is it? Well, all right. I think I have a diagram here somewhere. There it is. Okay. So the blue line is first you are spending a lot of expenses, so it looks like your productivity is really low, and then later you're harvesting it. So to me, it kind of looks like a J, so we call it the J curve. And to be a little bit more formal about it, well, so if we want to extend Halton's theorem, we have these first two things I just mentioned, but now we also have to consider that these complementary investments are going to take time, so you stretch it out over a little bit of time as well. So the growth accounting needs to be updated. So here's one way to think about it. The basic, this part of it looks a little complicated, but it's just the traditional sort of solo accounting. You've got the change in capital multiplied by the rate of return on capital. N is labor in this case, the change in labor by the thing. That's the traditional amount. But now you've got a new term, which is how much of these intangibles. The lambda over z is how much intangible you get per unit. And that's going to be important. And so if you subtract the true output, the measured output from the true output, you get these three terms here. And this basically tells you how much mismeasurement, to answer that question I described to you qualitatively before, but you can be a little bit more formal. Lambda is the amount of intangibles there are for every unit. So the ratio there, if your intangibles if it's exactly even, then this cancels out. This number here is how much intangibles you're investing. If it's got a high ratio, but you're investing nothing in intangibles, then it doesn't matter. It's that, you know. And then the last one is the relative growth rate. If they're growing at exactly the same rate, like I said before, then they also cancel out. So if any one of those terms is zero, then you have no mismeasurement. But if they're all positive, then you're going to have creating more output, more intangible output than what you're counting. And during the build-up phase, while you're creating this stuff, then these numbers are all going to be positive, and they actually could be pretty significant. So I think, yeah, here's how we calibrate it. So in the productivity J-curve, which I guess is in your readings, you want to flip into it. This chart comes from that. This magenta line is the official numbers on TFP growth in the US economy. The blue line is our adjusted number, and that consists of two parts. The dotted green line is the extra intangible assets that have been created. So that moves it way up. We're creating all these assets that we now benefit from. But then you also have to subtract that we're using the assets we created last year or the previous years. So that brings it down. And you net out the green and the red, I guess, you get this the blue line, the adjustment there. So net, by my estimates, the US economy is producing a lot more output than what we officially say. Much of that is this software and other intangibles that we're all benefiting from. It's not on the books and the GDP or other places the way it should be, especially the business process redesign. But if we were able to measure it more carefully, we would see that there's like 15% more output than what we thought. Yeah, go ahead. No. So it depends on whether it was accounted for as an expense or an investment. If it was counted for as an expense, then it seems like we're like, let's just like make a concrete example. You've hired this consulting firm to help redesign the factory. And so you're producing 100 computers. The consulting firm comes in and helps you redesign the factory. You're still producing 100 because they haven't successfully redesigned it yet. They're in the process. Now your books say, oh my God, you're spending even more than you did last year. Same amount of output. Your productivity going down. You're spending on all your workers, all your energy, all your equipment, plus these guys from consulting. It's pushing down your measured productivity. Well, no, that's an intermediate input. That's going to be, so GDP is final goods. And if you have intermediate goods, those don't get counted. So if like using like steel or consulting services or whatever else as a business input, then they get paid as output. You subtract it as an input, so those wash out. So yeah, all the intermediate inputs, there are a plus and a minus, so they cancel each other out. It's only the final goods that add up to GDP. So it looks like your total output isn't any greater. Now, another way of thinking about it, which I think is more correct but much harder to measure, so I don't blame them, is that what the consulting firm is doing is it is building an invisible factory that none of us can see. But we know it's there because when it's done, we're going to produce more output. It's not made out of bricks and mortar. It's made out of business processes, which are very hard to touch. But they're there. They're real. They're just kind of invisible, intangible. And if we were to measure them, then we would say that at the end of the year, you have 100 computers produced, plus you have, whatever, $10 million worth of intangible assets that have been created. And so your output actually went up. And so those consultants weren't doing nothing. They were building something, just happened to be invisible. Is that too abstract? Does that make sense? Yeah. And then the next year, the consultants leave. You've still got this invisible factory. It's churning out 110 computers. And you're like, wow, productivity. So I have, where's the J curve? There it is. Productivity is like way up. How are you getting all this like free computers? Well, they're not free. They're from this intangible asset that you're depreciating and you're using. So, yeah, I mean, to me, if you think of it as analogous to a factory, a physical factory, then it just happens to not be measured very well. But if those guys were coming in and building a factory, you would count them as producing output. It would be this output there. Yeah, go ahead, Arjun. Yeah, well, by our best estimate, at least up till 2020, I mean, it's all been mismeasurement the other direction. I think I have it here. I don't have it here, but in the paper itself, we do have some examples of some earlier ones that kind of turned the corner. But right now, we are still investing. We're creating more intangibles than we are using. It's still a net plus, net plus to the asset side. But in a way, that's good news. It means that we sort of have this potential return that we should be getting later. So I have made a bet with my friend Bob Gordon that the second half of the 2020s, we're going to start harvesting some of that stuff. But I don't know. Then right now, they want to spend another $1 trillion on the data centers. So they're like all in on driving this, But if they're rational, it's a big if, then we should be getting some of those returns later. If this, by the way, this all assumes that, when they make the investment, they're going to get the return later, that they're not being idiots. Sometimes they are idiots. Sometimes you get way less back than what you put in. Sometimes you get way more. I'm going to take kind of an efficient markets hypothesis, say that on average, I'm not going to say that they're overestimating. If you just take them as sort of neutral, that on average, they're going to get a return on that, then we should expect greater returns later. But we're not seeing it yet at least when I wrote that paper, I have to go back and check the numbers to see if there's any turning. But yeah, that's the right way to think about it. So so a number of you had questions. I'd be very happy to just take the questions, more broadly, but speak so everyone can hear the answers. But yeah, go ahead.
I was going to ask, so the Holton theorem is very local, and I
yes.
understand where does it start to become computation.
Yes.
Just one quirky question is applying the Holton more or less like applying the electrical model the same.
Yeah. I think that's a very fair and recursive answer. I think that I find the Holton theorem, most plausible for small changes, 1 or 2%, and then the kind of like local effects. But if you're having like this radical 30% or 100% change, like we saw in some of them, then you would expect all sorts of other changes in the economy that are complementary and spillovers. And so, in fact, one slightly ad hoc way was I showed you that we could add complementaries and spread it out over some period of time, and that would be part of it. But a more principled way would be thinking about trying to understand what those second order effects are. Some of them, may be positive, nonlinearities that are convex or concave, and you have to think, it obviously when you start taking it to second order effects, everything gets like much more complicated. So I think that a fair concern is that this is sort of a kind of simplified base case. Yeah. How about right here? Sorry, say your name again.
My name's Joe.
Yeah.
I'd like to know. So you said you made the bet with the one. What are the stakes? And two, to see if a particular reason that he's sort of bearish on AI.
Yeah. So you can go to longbets.com. You can read about it. The stakes are very high. It is a dinner I think it's like a $300 dinner. I don't know, something like that. No, I take it back. It was going to be a dinner. We changed it. It's a donation to give directly or some charity. Turns out we're both giving to the same charity, so they win no matter what. Yeah, he's just, I mean, he's got a great book called The Rise and Fall of American Productivity, which is, 90% of it is just awesome. And then you see what's coming. The last 10%, he sort of talks about the future, and he's just a grump. I just think he's kind of a grump about it. And he's just like, we've known each other for like 20 or 30 years. We have dinner together all the time. And he's always like complaining about the airlines or about email or whatever.
That's why you switched.
Yeah, maybe about the dinner. No, I like having dinner with him. I actually, he's really fun. But he just, and he's, he's actually very good at using computers and technology, but he just has sort of this pessimism. I think also, I mean, he makes a good point, which, a lot of people, younger people tend to overlook, is that there are some very amazing inventions in the early part of the 20th century, penicillin, electricity, car, radio, television. And what he will point out accurately is that this is not the first time we've had amazing inventions. And these other amazing inventions were also very important, and he would say even more important. So I think his basic attitude is, AI, the internet, it's all nice and good, but it doesn't compare to the great inventions of his generation. That's sort of a subjective thing. I think nothing wrong with like the car and airplanes and all that stuff. But like I said on my first or second slide, if you could actually solve intelligence, like how much bigger can it get than that? Like that's like, to me, that's like the ultimate. So maybe that's just a gut feel. So we'll see. Our bet is that, to be very precise about the bet, the Congressional Budget Office, when we made the bet, and I think it's still true, predicted that productivity growth for the rest of the decade was going to be 1.4% per year. And they used a very sophisticated methodology of basically extrapolating from the recent past. So fair enough. I go around hanging out with all these people in Silicon Valley and San Francisco, and I'm like, wow, there's some really neat things coming in the pipeline. We can do better than just extrapolating. And so I bet that it's going to be at least 0.3% higher than that. And he bet that it's going to be, I gave him 0.3% for free just to be nice. So if it's less than 0.3% faster than the Congressional Budget Office, he wins. If it's more, like 1.7% or more, then I win. I guess we'll find out in 5 years. Yeah. So far, I think I'm slightly ahead, actually, if you just look at the latest numbers. And the best is yet to come, I bet. Unless like the world gets destroyed or something, which I guess is a non-zero chance. How about right here? Yeah. Well, this could be a very long answer, so I'll give you sort of a somewhat abbreviated one. But it's an important question. So there's different ways that people measure intangibles. Some people go and kind of like try to count like how much time people say they're spending on intangibles. What we do in most of our papers is we look at the stock market. And you guys know Tobin's Q, the ratio of intangibles to tangibles, that number has grown a lot lately. So the basic assumption is that the investors are doing their best to be rational and estimate what the true value of a firm is. I'm not saying they always get it right. They clearly don't. But I'm not able to consistently beat them. So I'm not going to say that they're always overestimating or always underestimating. So if you assume that their estimate is a fair estimate, you can look at how the market value of the firm changes. And the basic equation is that the market value of the firm, like the value of all the debt and equity of the firm, is equal to all the assets of the firm. Kind of a definition almost. And those assets could include the physical plant and equipment. They could include the patents and IP that they own. They could include the intangibles that the firm controls. They don't include the employees because we don't have slavery, but they might include some firm-specific human capital. And so what you can do is you can look at when a firm invests more. I wish I had a whiteboard here, but I'll just do it with my hands here gesturing. When a firm invests more in, say, computers, what happens to market value of the firm? What you find is that in most cases, when one more dollar of any physical asset is associated with about one more dollar of market value. Computers, interestingly, one more dollar of computers is associated with about $10 of market value. It's not a free lunch. It doesn't mean you can go out and buy a computer and then you get $10 of market value. Our interpretation is that whenever you see $1 of computers in the company, there's another $9 that you don't see of intangible assets. So a computer on the loading dock that has not yet been installed might cost whatever, $3,000, a personal computer. But once it is integrated and being used, there's all this business process and everything. Now there's like another $27,000 worth of intangibles to make that computer useful, installing it and getting it going. So that's the basic idea. And so if you look at the market value of all these firms, you can estimate how much intangibles are being created over time. And what we see is that there are certain assets that are associated with much more, certain investments that are associated with much more. Another slightly, that's probably the more intuitive way of thinking about it, that there's this $9 of intangibles for every dollar of tangibles. A slightly more sophisticated but subtler way is that there's an adjustment cost. And when you install the computer, it takes a lot of effort. And it takes so much effort that by the time you have it installed, for somebody else to replicate it, they would have to spend $10. You may have one computer that's fully installed and integrated. They may have one computer that's sitting on the loading dock. In order for them to be where you are, even though you have the same computer assets, they are not the same as you because they haven't taken the time to install it. And that's going to take them a year and a lot of effort. And so the shadow value of your computer is $10 compared for every dollar that they have. Either way, it's sort of, two ways of thinking about the same thing. The net effect is if you do this, and this is done in a couple of my other papers, then you'll get an estimate of more and more intangibles being created in the economy. Okay. Next, a couple more questions. Let's see. I already got you a couple times, so I'm going to go over here, and then we'll go back to you, Max. Go ahead. Yes. So if you had a one-time shock, like electricity, like I don't know how much it's improved, like how much more sophisticated, but basically electricity is a lot like what it was in 1880. Like, I don't know, maybe they have better AC or transformers, whatever, but it's basically kind of the same. So that would be like a one-time shock. Computer software is just wave after wave. Moore's law has an improvement of computer hardware of about 10x every 5 years. And software is also improving quite rapidly. So this is really a whole bunch of J-curves, one on top of each other. If progress stopped in software and computers, then we get it back. But this is just a whole bunch of them, one on top of each other, each one bigger than the ones before. So we are just keep piling up more and more. We are getting some of the returns on the earlier J-curves. Back here, like when they introduced word processors and spreadsheets, if we just stop with that, we would see it come back up. And then they introduced internet shopping. And if they had stopped, we would have just gone up. And then they introduced, ERP, enterprise resource planning systems, and, all these other things. And every time they're introducing them, you're getting another one that's even bigger than the other ones. So it's good news. We have, if this is right, we have a bunch of stored up J-curve that we're going to be harvesting over time, about 15%. Yeah. That make sense? Yeah. Okay. In the back, yeah? Maxime, I think. Well, it depends. So I think depending on why they didn't do it, okay? I mean, one of it may be that they hadn't figured out the complementary investments. It took a while. Remember that story I told about electricity? There was like debates you could read about, like trying to figure out. I think you call them complementary investments. You could also call them co-inventions. Tim Bresnahan likes to use that term, and I like it. It's basically some people invent this amazing, software or electricity, and other people invent a new business process to go with it. I mean, we did it just in class here. We were just talking about that when you have the more skilled workers sharing their knowledge with the large language model in the call centers, it would be smart to co-invent some new incentive systems to reward them. Because if you use the old incentive systems, you may actually be counterproductive. And you can imagine situations where you actually make things worse off if you don't change your co-inventions. So then some economist or entrepreneur needs to think of a new one. And those co-inventions in practice, in the US economy and every economy, Joseph Schumpeter would argue happen more from selection than from adaptation. So it's not so much that big companies, that the railroad companies figure out how to use cars. It's that the railroad companies do what they're doing, and then some new companies come along and introduce cars. And the companies that do mini computers, it's mainframe computer companies, even like within a technology. So there's a lot of creative destruction as people explore. And here in Silicon Valley, you talk to Vinod Khosla. When you guys get a chance to do this sometime, if he makes 10 investments, he's hoping one of them will be a home run, and 9 of them he's like not necessarily expecting to play out. He doesn't even know which one's going to be which. And the great thing about capitalism is you can have all these things going on in parallel. And maybe the entrepreneurs, they're all very confident of their idea, but it's not necessarily something you can just sit down in a room and figure out in advance. You have to kind of go out and try it. And so that's the process. And it turns out sometimes that some counterintuitive things, some counterintuitive co-inventions end up being really valuable, and other ones that you thought would be right end up not being valuable. So you just have to experiment. And that's kind of my model of what's going on. And so you just have lots of experimentation. I mean, to that point, by the way, the US economy, we've invented some amazing technologies, many around the world, actually, I should say. But just looking at the US for a minute, dynamism has gone way down over the past 20 or 30 years. If you look at the number of new companies less than 5 years old, the number of people who are moving from one company to another, all the amount of mobility from one region to another, all these metrics of dynamism, John Halterwanger, Steve Davis have documented that they've fallen a lot. And so that is, to me, a bearish sign on co-invention, because even if you have engineers coming up with new technologies, if you don't have dynamism and entrepreneurship and new companies being formed and existing companies rearranging, you're not going to be able to get those complementary investments. And I think most people underestimate how important those complementary investments are. You guys are economists, so you guys can take them more seriously, but a big agenda is to figure out ways of identifying those complementary investments, or perhaps even more importantly, creating meta institutions that allow us to speed up the invention and discovery and diffusion of those complementary inventions. And that would do a lot for productivity growth. Okay, take another question. I'm going to plow ahead a little. Go ahead. Well, this is the productivity J curve. So this is looking at inputs and outputs. And I would say the J curve would go away if you measured all of the capital outputs correctly, tangible and intangible. Then all those investments into capital assets would show up instantly, not as more consumer goods, but as more capital assets. And the net total would be going up just as the inputs were going up. And then later, when you were harvesting them, you would be charging as an input the rundown. So you could make it go away if you did the accounting differently. Yeah. But what is capital? If capital doesn't include the intangible capital, then you're going to get the wrong numbers, both in terms of the capital increase and the capital down. So it's are you measuring capital correctly? That's the way I think. The way I think of it is that we are taking some things, we are charging them as expenses, and they should be counted as assets. Now, to be a little bit more precise, there have been improvements over time. It used to be that all software was expensed, and now they will capitalize a lot of the software in the GDP. And most business processes or investments are still expensed, but you could have it capitalized. Human capital, like education, I should check this, but I'm pretty sure that's not capitalized. So you could imagine if I don't blame the people who do the national accounts or the accounts in a particular firm, because there's always a trade-off between precision and accuracy. And you don't want the CEO or the president or whoever saying, "Oh, we created a ton of these intangible assets. You can't see them, but they're there." That may give too many degrees of freedom to the executives. And so accountants tend to say, we want to be a little bit narrow about what we're willing to count. But as an economist, you may want to have, a broader dashboard. One more question. Go ahead. I don't think that would matter to a first order. That's sort of like how you capture the thing. I mean, okay. I guess it matters in this following sense that if I'm measuring the intangibles by the stock market or the market value of the firms, then there has to be some story later that the investors are getting some of that back, either through dividends or capital gains or something. So when they are willing to put these very high market values on companies that have very low physical assets, the way I think of it, there's two ways that are equivalent. One is that they are expecting the net present value of future cash flows to be high, dividends, etc. Why are they expecting all those cash flows? Well, another way of interpreting it is that they think that firm has something, some magic that's going to generate all these cash flows. We could label that magic intangible assets. It owns something, right? It must own something because they're willing to pay for it. It has to be some ownable non-human asset that they can capture a share from. So whatever it is, we will call that intangible, and then it all adds. All right, let me plow ahead. I want to leave a little time at the end just for some broader questions too. These are some great questions about this specifically, but I'm just going to touch on a couple other things, and then we'll have more time for even grander questions if you want. So we've started trying to look at some of the AI. For the J curve, the paper you had was computers, R&D, software. We didn't have AI in there because there wasn't much, but we're starting to do it with these MOPS survey, the Management Organizational Processes survey. Unfortunately, I just found out that they've canceled the MOPS survey. We raised $1 million for the next wave, which is supposed to be in 2026, as it says over there. We're working on getting it reinstated, but the government is going through some weird things right now. So we do it jointly with the government. It's really great to do it with the government because I could send out my own survey, but as Nick Bloom likes to joke, I'm going to steal his joke. If you add these 6 words to the survey, it massively increases your response rate. So try this. Your response is required by law. Massively helps. So, but only you can do that if you do it with the government. At least I believe so. So we are finding, with my paper with Christina McElhern and others, we are finding some evidence of this J curve. We found that there was sort of a negative effect initially, and then a greater effect. So that paper, it's called what do we call it? Micro Foundations of the Productivity J curve. Yeah. So putting this stuff together, and then we'll talk a little bit about the futures. So here's some back of the envelope estimates, and we're working on refining this a little bit more. Paper with Phil Barat, who I think you're hearing from tomorrow, and Basil. We're kind of working some stuff. So here's some just very rough numbers. Don't quote these. But suppose that you looked at the task exposure, how many tasks are suitable for large language models and other things. Something in the neighborhood of 38% according to these different studies. Maybe 88% of them are cost effective to be done of the 38%. So you multiply those together, maybe 33% is that first part of Holton's theorem that could be affected by these. Productivity improvements, well, these are all over the place. So if you go by our paper or the other ones I put up on that screen with lots of them, anywhere from like 27 to 100%. If you multiply it by the 33%, you get from 9 to 33%. So that's how much Holton's theorem would predict that AI would boost output by 9 to 33%, way more than Daron Acemoglu or other people got. So we have some different numbers when we do our analysis. But as I just said, you got to spread that out. It doesn't all happen in 2025. It could take 10 years for that to happen. So now you take these and multiply them by 10%, 1/10, and you get something like that per year. Pick a midpoint of 2.1%. And now I win my bet with Bob Gordon. If these numbers are right, we'll get another 2.1% of productivity. But that's sort of like what we're trying to refine those numbers a little bit. But I just wanted to, for fun, give you a sense of where we're going. Yep.
Give the 10-year.
Yeah. So right off the bat, so part of the reason we have bigger numbers is we're using more recent models of LLMs, but then on top of that, they're going to keep increasing. So this so far isn't accounting for that at all. But as they improve, now think about it, those improvements are going to affect more of the future years than the current year. So it's going to, push out the longer your time window, the more important those improvements are going to be. Let's do that a little bit. So two things: the AI is going to improve itself. It's also going to improve all other inventions, because AI. One of the things that AI can do is not just boost call centers; it could also boost R&D productivity. So it's a method of invention. Daron doesn't assume that we're doing that, neither do most people. But if R&D is the primary driver and LLMs can affect the development of new ideas, I'm sure you're going to talk about that in some of your later sessions, then you can start having an increase in the rate of growth as well, because you're getting more new ideas every year. It's not going to affect the first few years much, but over time, in the out years, that becomes really dominant. So that's going to be a big thing. And then there's AI itself is getting better. And have you guys seen scaling laws? You guys know what that is? Yes. So, if you increase compute, data set size, parameters, so far there's been this empirical regularity that's like a remarkably straight line, that the LLMs perform better and better. They have less and less test loss. And that test loss is pretty closely correlated with all these other metrics of performance, like scoring well on those tests, on those benchmarks that I put on the first or second slide. So Dario Amodei and others are, betting on this, that we just keep going down that scaling law, and we'll get more and more powerful AI, and then we'll have, GPT-5 and GPT-6 and, Gemini 2.5 and 3.0, et cetera. So that could start leading. Yes, go ahead. Yeah, we didn't really talk much about that, but yeah, that's part of why these complementarities are there. Is that Le Chatelier's principle will, if you speed up one part and don't speed up the components, you're not getting the benefits. So that's why we're spreading it out over 10 years. And you could also have relatedly Baumol type effects, where the more and more of the economy is in the slow growing areas. Baumol's effects are not a law. You could have the sectors that are having faster productivity growth grow. And lately, we've been seeing a bit of that, where, one slightly, staggering statistic is that last quarter, I'm told, I need to check this, more of GDP growth went into data center construction than into total consumption increase. So not levels, but changes. And likewise, the amount of money on data centers is approaching the amount of money going into office buildings. So you could have this sector with very high productivity growth also growing very rapidly. And then you have a reverse Baumol's disease. Now you have the faster growing sectors. And it's going to depend on the elasticities, like I said earlier. So there's no law that it has to go that way. But if we're lucky, what we'll see is that the sectors with high productivity growth have steady or even growing shares of the economy. So that's what a lot of these the folks who are investing in the data centers are betting, that they're trying to draw more resources into these sectors that are growing very rapidly. And then that leads to potentially, this really exciting idea that gives rise to the singularity, that the AI is used to create more AI. AI is made out of code. And so if the AI can improve itself, then you get faster and faster progress. By some measures, about 30% of the code at leading AI companies is AI generated. Chips are increasingly AI designed. So if you get recursive self-improvement, then you get a whole another kind of growth that we've never really had before, that would really start taking off a lot more. But that gets exciting. That's a little bit further out there, like maybe not way out there, but 5 or 10 years out there for that start being important. So what we may be approaching, and this is the way Dario Amodei defines it in his essay, Machines of Love and Grace, is that we could get Nobel level expertise across many fields, fully digital interface that controls a lot of things, so a lot more agency, you could have millions of instances. It's not just one expert, but you can replicate it and have them all be working in parallel. Someone mentioned they could work a lot faster, even if they weren't smarter, but they may also be smarter. And they may be able to carry out tasks. You could have them control robots. You could have them run laboratory experiments. That starts getting to be, pretty interesting when it comes to economic growth. Dario and others think that it might be, in 2027, 2028. We just talked about how there may be some bottlenecks, so it's not going to be an instant transformation. And I think there's a very interesting economic agenda, on the right side over here to think through what are those implications, what are the potential bottlenecks. That is really where it starts getting interesting. If the AI folks succeed in the stuff on the left hand of the side, what does that mean on the right hand side? So one of the reasons you guys are all here is to address that. And one of the things that I'm trying to do is create more of a community around this. And that's why I'm so happy that Phil's teaching this course. We had a retreat last year at Asilomar, which isn't far from here. And we brought together about 40 AI researchers like, Rich Sutton and Tom Mitchell and Joshua Bengio and Peter Norvig and a lot of other folks like that, with a whole bunch of economists like David Otter and Susan Athey and Joshua Gans. You can see there. I guess you may recognize a lot of those faces there. And what we're trying to do is create a community of people to think harder about how this technology is going to change the organization of work. You guys in this program are part of that agenda. We're going to have an NBR workshop in September where a subset of these folks are each presenting papers on this. We're going to have another conference in December where we bring in the general public more broadly. But the specific research agenda that Anton Koronek, Ajay Agarwal, and I are writing up is to define, currently we have 8 major areas of research, and hopefully some of you will be working on each of these. I'll send you a copy of this paper. It's not quite ready for broad circulation, but I'd love to get your feedback and comments on it. I guess I'll just give it to Phil. Phil helped with writing drafts of it. So, but that would be a good thing to get you guys feedback on and different things to work on. So as I'm about out of time here, let me just summarize a couple of key points, and maybe we'll have time for a minute or two for questions. I think AI is the most general of all general purpose technologies, and those are really important. Its effects are going to be a function of at least these 3 things: the task it's going to affect, which is growing more and more, the productivity gain in each task, and then the adjustment costs or the intangible complements that spread it out over time. Each of these factors are pretty large. So my best cut, or our best cut at the back of the envelope, is that the ultimate effects are going to be pretty large, but the lags are important. They'll be spread out over time. In addition to that, it's a new method of invention. It's allowing us to invent things more in R&D, and it'll have, and one of the things that it'll invent is better AI, recursively improve. And I just say, once you start thinking about all that, that seems like the most important question on Earth today. So I'm glad you guys are all working on thinking about it. Thanks very much. So I've left just a couple minutes if you guys have any last questions or comments. Yeah, right here. Are you done? Right, the measured. The real one is the one that includes it, in my opinion. But yeah, it's larger than the measured one. Yeah.
Yeah. So from.
Well, I think it's more just that there have been different waves of this. Computers are different than a lot of other inventions in that they just keep getting better. Andy Grove, Intel CEO for a long time, basically said that every time you have a 10x improvement in something, you're in an entirely different world, a new regime. And back of the envelope, computers have a 10x improvement every 5 years. So we've just had wave after wave after wave after wave of these. So it's probably more properly thought of as just a whole bunch of these J curves, one on top of each other. Well, we are reaching the upper part of the previous J curve and getting the returns from that, but then there's another one on top of that. So we are getting the returns from from word processors. I think we've kind of maxed out. Maybe there's more room for word processor improvement, but we basically, when I was a kid, we typed on typewriters. Okay. And it was a big deal when we had a computer to do a word processor. And then that diffused. And now I think it's pretty much, I guess you could do voice dictation. I don't know. I guess maybe there's still some improvements. So that one, we're harvesting the benefits. And then spreadsheets, we're harvesting the benefits. And so each of the earlier ways we are fully harvesting the benefits of, but there's other ones that are even more important. And that's why that line kept going down. Maybe I left it on the screen too long. I don't want to have you over-index on that. I don't want you to have the impression that, the good news is that there's even more, every year there's more intangibles. The amount of intangibles assets is growing faster than the amount we're using. So we are using last year's intangibles, but we're creating even more. And so the good news is, if you believe the J-curve like I do, that we have a lot of latent output that we will be able to harvest in the coming years. And we're harvesting some of it. We're going to harvest even more. Another way to think about it is if all technology just froze, like all the machine learning people just decide to go on vacation, all the computer chip companies say, you know what, we're good. We're just going to stop with this level. All the AI and computer technology just stopped right where it didn't get worse. It stayed where it is. That we would have a decade or more of growth taking advantage of what's already been invented. And we would get that upward part and we would harvest it. Then, and then we would capture that. Does that make sense? But the good news, but what even better than that is that we keep adding to the intangibles. So 5 years from now, we're going to have even more. As long as we keep inventing stuff that and having these investments in intangibles. Yeah. So that's that. Yeah, that didn't happen with electricity and didn't happen with other things, but yeah, for AI, it does seem to be happening. Okay, one more question. There's different ways of thinking about that. I think it'd be great to do that very explicitly, like in the Acemoglu-Estrepo or the Zera model, where you have these new tasks. I don't know if you guys have seen that yet, but in there, you can explicitly add new tasks. You can also think of it more implicitly, like with the complementarities. I mentioned co-invention. You have to invent, or you have the opportunity to invent new things. I think those are incredibly important. And sometimes people talk about, it's not just like there's a certain amount of tasks you can invent every year. I think arguably the opportunity to invent new tasks is growing. A lot of people, Ben Jones and others, have talked about ideas are getting harder to find. And I think you can think of fishing out, like there's a lake with a certain number of fish in it, and those are the ideas. And as we get better and better, we fish them out. That's one metaphor. Another metaphor that I think is equally apt and may hopefully be more important in the long run is that ideas are like building blocks or like Lego bricks. And that the more you make, the more new things you can make, because now you've got these different components, you can put them together as you get combinatorial innovation. Like Weitzman talks about that. I mean, the reason that Mark Zuckerberg was able to invent Facebook, he didn't have to figure out how to invent the internet. That was already invented. He didn't have to figure out how to make wires. That was already invented. He didn't have to figure out how to smelt copper and take rocks and turn them into a conductive thing. All that stuff had been invented. And that made it really easy for him to create $100 billion worth of value because he was able to take these existing building blocks. And so I think that second story of building blocks is as apt as the first story of fishing out, depending on the different contexts. And in some places, it's getting harder and harder. In other places, it's getting easier, I think. And I wouldn't be surprised if in the next few years we saw a lot more opportunities for the easier. And so to your question, we'll see more and more new inventions, new tasks being created. AI will help us. A lot will depend on our ability to encapsulate the complexity of the old tasks, so we don't have to understand all of that. We can just use them as building blocks. That's my metaphor of creating new tasks from old tasks and combinatorial or recombinant innovation. So on that sort of hopeful note, I'll wrap up and say that I hope all of you guys have lots of fodder here to create some new ideas and to build on them. I'm sure you'll come up with some ideas that have never been seen before by combining some of the old ones and building on these tools. and wish you luck. I'm going to be around all week, so except for the next 2 days, but I'll be back for the second part of the week and next week, and I'm glad you guys are here. And in particular, I'm going to see you all, not this coming Friday, but the next Friday at my house. We'll have a little party to wrap things up, but I hope that I'll run into most of you before then. Thanks a lot for giving me a chance to share this research.